Okay, so off we go. Last time we were talking about linear approximations, and one of the very first things I said when I said, okay, let's think about linear approximations, I said, if it exists, right? And I pointed out that there are some concerns there as to whether or not there even is a linear approximation, and that we would come back and address that later. And here we are. So I want to entertain the question of whether or not the linear approximation formula we wrote down, does it always work? Are there some cases where it's a massive crash and burn failure? And I say the latter. So here's my example. Let's think about this function right here, which admittedly is weird. Weird is legal. Right? So it's a perfectly good function, frankly, and it's defined to be 0 most places. So over here in the first quadrant, the value of the function is 0. Fourth quadrant, the value of the function is 0. Likewise, third quadrant, second quadrant, everywhere except for on the axes. And on the axes, the value of this function is 1, which I'm going to represent, for example, on the x-axis, I'm going to represent the value of the function as being 1 by drawing this line up above the x-axis at height 1. So this is just the graph of the function, likewise above the y-axis here. This is the graph of this function. It's a little bit hard of a picture to draw, but there it is. And let's go in naively and just write down the formula for our linear approximation, and I claim it ends up being 1. Because the value of the function at the origin, the value of the function is 1. And if you ask what's the partial derivative in either the x direction or the y direction, at the origin now, right? Keep in mind, this is at the origin that we're interested in. Right? At the origin, the partial derivatives are 0 because, look, you can see it's not changing at all as you go in the y direction, and it's not changing at all as you go in the x direction. So those partial derivatives are 0. And then you plug that into our previous formula for how to do linear approximations, and again, as I had said before, that linear approximation is just, I'm going to kill all this, is just 1. Now, is that a good linear approximation? Is this a success of that formula, or is this an embarrassment of that formula? And, okay, well, let's think about it. Here's what 1 looks like. Right, 1, it's got the value 1 everywhere. It's just going to be basically the plane containing these two elevated lines on the graph. And, okay, well, how good of an approximation does that do as I, for example, approach the origin, let's say, from somewhere in the, somewhere in the first quadrant, whatever. Well, the value of the actual function, right? And again, let's think about our actual function. Our actual function is 0 the whole way along that path, all the way toward the origin. And yet, the value of this linear approximation is 1 everywhere along that same path. So is 1 a good estimate of 0? No, it's poor, right? Very bad estimate. And so this is an unacceptable attempt at a linear approximation. And again, that should be a little bit unsettling because we followed the formula. We did exactly what we derived a couple days ago, whenever that was. And yet we get this clearly unacceptable nonsense. So this is a legit concern, right? Again, we were worried about what might happen, and it happened. So this is not a good linear approximation. Our previous formula does not always work. It only works sometimes. So we need to figure out how to be somewhat clear about under what circumstances does it work. I mean, let's think about that, just stepping back for just a moment. Could we just say, sometimes you lose, right? What good is it to have a formula that allegedly approximates something if we have no idea when it's useful. Right? If you don't know when it's going to work, then you can never have confidence in your answers. And this is just not okay, right? This is unacceptable. All right. So we're going to try to develop some sense of when these kinds of problems happen. And first thing I'm going to do is I'm going to show you something that doesn't work. And I'm going to show you what doesn't work because it seems like it really ought to. And it's important that you realize why what seems like it ought to work doesn't work. So seemingly reasonable first attempt is to say, okay, well, let's look at the error in the approximation. Correct value minus estimated value, that's error, right? Maybe it's good enough just to say that the error needs to approach 0. And this is very tempting. Right? The temptation is, well, error is bad, and bad is something I want to go away. So it seems like if the error goes away, then shouldn't that mean that everything's good? And it's very tempting, and it just doesn't work. And easy to show that it doesn't work because let's see. Let me do that. I'm sorry.
If you scroll a bit, sorry.
Oh. Okay.
Thanks.
Yep. Yeah. So So let's just easy example of how this fails to work. Let's look at this function right here. That's unassuming function, right? There's nothing obscure about that function. Here is what I'm going to call a candidate linear approximation. Obviously not good, right? Nevertheless, someone could come to us and say, "Hey, I think this is a good linear approximation. We should entertain whether this is a good linear approximation or not." Now we can graph these, no problem. There's our original function. Here's our candidate linear approximation, and you can see it's just not even close. It's ridiculous. It's hilariously bad, right? The question is not whether this is a good linear approximation at this point. The question is, does this requirement, that error approach 0, does that successfully eliminate this obviously bad linear approximation attempt? And it doesn't. It doesn't eliminate anything because here's your error, right? It's 5x minus 3x. Correct value minus estimated value. And that error, you can see it happen right here in the picture. That error indeed does approach 0. So simply requiring error approach 0 allows obvious nonsense to, pass itself off as being a linear approximation. So clearly bad, not good enough. Here's the replacement concept, the replacement test. Again, our goal here is to eliminate bad linear approximations, right? And I claim what works very nicely is this thing called relative error. It's not just a matter of how far off are you in the output. It's that divided by how far away you are in the inputs. So it's error divided by the distance from x to a. Now, there's again lots of things to say about how this is dealt with in a multivariable context. We don't have time to go into all that. By the way, you're not responsible for all of that either. But I just want to show you how well this works in a single variable context, and I'm going to ask you to trust me and the book that it works very nicely in the multivariable as well. So here we are, back to our same original example. There's a function and its graph that we want to approximate. Here is our candidate, our hilariously bad candidate linear approximation that we would like to eliminate. And let's look at relative error, keeping in mind that the formula for relative error, it's not just the error. It's not just that vertical distance. It's that divided by x minus a. Right? It's this divided by that. And you can kind of even see it happening in the picture. You could probably make like a similar triangles argument or something as you approach the origin. Not that you have to. You can straight up do it with the algebra. and this relative error does not approach 0. So if we simply require that relative error should approach 0, what we call vanishing relative error, well, this does not meet that requirement. It obviously approaches 2. And that, as it should, eliminates this ridiculous attempt at a linear approximation from being acceptable. So vanishing relative error is the test that we need. Now, what does that have to do with all of this? Oh gosh, highly opaque, scary-looking stuff. Yeah.
I just have a question.
Yeah.
Just previously. So
Yeah.
If for the relative, not the relative error, the error when we said would it change anything if it approaches 0? We said
Yeah.
no.
Yep.
So in this case, it shouldn't. Like, is it good that it's not approaching 0 and it's approaching 2? Or?
It is good that it's not approaching 0 because, so remember, the big idea is, the test that we were proposing here is, hey, look, if the error goes to 0, good enough. And I claim that this shows why, no, it's not good enough because, look, this error approaches 0, and yet that's clearly not good enough, right, as a linear approximation. So it's good that this does not approach 0 because the test was, look, if the relative error approaches 0, then we like it. This one didn't pass the test. So according to our test, this is not a good linear approximation. And that's, I think, a very fair statement. That's definitely not a good linear approximation, and this detected that. Is that cool?
Yeah, thank you.
Yeah.
What is the point of limit x approaching
0? So the idea is that we're keeping track of. Oh gosh, where's my? We're trying to keep track of what happens as the point where you're doing the approximation approaches. The point where you're evaluating the approximation. Let me circle the correct thing. The point where you're evaluating the approximation approaches the point where you're actually basing your linear approximation. And so, so we're interested in the limit as we approach 0. We can't say, evaluate at x equals 0, because if I evaluated when x was a, that would have a 0 in the denominator, and that's just, you can't do that. Is that cool?
But in the denominator, you just didn't write the minus a. Why is that?
Oh, because a is 0. And I did write the minus a, but it just turned out to be 0. So, yeah.
Oh, okay.
Is that cool?
Yeah.
Okay, yeah, yes.
So why did you take the length or the magnitude of x minus?
Because I want to be able to divide, and you can't divide by vectors. And because, because this is what works.
Okay.
But one of the things that makes it work is that you're actually legally allowed to divide by magnitudes, but you're not. There's literally no such thing as a division by a vector. There is no such construction. So yeah. Okay, so what does this have to do with all of the scary-looking formalities here? And I think, in fact, even the way I've written it here is a little bit less scary than the way it looks in the book. And the answer is that, that's really all this is saying. This is saying relative error approaches 0. I've just rewritten error as f minus L, namely true value minus estimated value. And I've written L as the formula that we derived last time for L, our candidate linear approximation. Don't forget to distribute the minus sign, so this becomes a minus. Really, that's all this is, right? So that it always mystified me when I first saw this. I'm like, it's weird that there's 3 terms there. I feel like there should be 2 terms. I don't know. It just never really quite settled for me until I eventually kind of broke it all down and slowly and carefully, and then realized that this is just all this monstrosity on the right is just a way of rewriting relative error, and we simply want to require that it approach 0. So that's why we use this as a definition of differentiability, and differentiability is synonymous with the linear approximation is a good linear approximation. It's because this says vanishing relative error. Okay, one last little thing I want to mention, and that is that you can rewrite this numerator. We've seen it here. Excuse me. We've seen it here as being true value minus approximated value. But again, distributing the minus sign. I want to interpret it instead as being this minus that, because both of these things have names. Now it's just a different way of writing it. Okay? This thing on the left, f of x minus f of a, says how much did the function actually change? The honest, true change in the value of the function, and this is what we call the increment. It's just a little bit of terminology. It's a good word to have, though, so you don't have to constantly say f of x minus f of a. It's just a mouthful. Okay. The thing on the right, this is, it's not the linear approximation, right? But it's our it's the part of the linear approximation that's representing our attempt at understanding how much the function changed. So it's our linear estimate of the change. And there's a standard term for linear estimate of the change of a function, and that term is differential. And y'all have seen this notation before, df. So in general, differential just means a linear approximation of how much a function actually changes. Okay. All right, so heads up about those words. And with that, we're done with differentiability, and off we go to the next thing, which is actually related. We're going to talk about continuous differentiability. Now, semantically, you would think that this would be an obvious refinement of differentiability. It's not. It's a completely different thing. Continuous differentiability does not make any reference to differentiability in its definition. Here is the definition. Functions continuously differentiable, you tell by looking at all the partials. Partial derivatives are easy to compute. You don't need a function to be differentiable to compute the partials, right? There's plenty of functions where the partials exist. The function's not differentiable. So continuously differentiable just requires that the partials exist, namely that there's no like division by zero, log of a negative number, no explosions, right? No fiery catastrophes. And secondly, we require that they be continuous. Okay, now that's, again, where does it say relative error? Nowhere. Continuous differentiability is not based on the idea of differentiability. And here's the really good thing about continuous differentiability. Look how easy it is to check, right? You just have to look at the partial derivatives. World's easiest derivatives to compute, right? Just check if they exist, right? Check that they're continuous. Okay, there's some, if we wanted to be all rigorous about it in this class, then we would get upset about exactly how do we define continuity. It's not what this class is about. I'm going to say we're going to just recover, and this is true, by the way, old facts from single variable calculus. And basically every function you've ever written down is continuous where it's defined. Right, now you may be thinking, what about tangent? Tangent's got a wild discontinuity. Yeah, where it is not defined. Right? But trig functions, exponentials, logs, rational functions, anything that you can think of pretty much, wherever those functions are defined, they are continuous. So again, I'm going to say also pretty easy to check, right? Anything you've ever written down, unless you've written down the heaviside function, that one's not, right? But other than weirdo stuff like that, standard algebraic, normal, regular, good old high school type functions are continuous where they're defined. Okay, so totally different concept. Why do we care? We care because of this theorem right here. And the theorem says that if the function is continuously differentiable, Again, easy to eyeball glance. If it's continuously differentiable, then it is differentiable, which is that scary concept on the previous page with relative error and multivariable limits and all the yikes that would go into. That's a really hard expression to deal with. Right? So we get to conclude something that would have been a huge amount of trouble, and we get to conclude it based on looking at a very easy to check, easy to define concept, namely continuous differentiability. So here's an example how we're going to use this. Let's look at this example right here. Example, is this function differentiable? By the way, feel free to take a look at my old exams. I hope everyone's noticed by now that I have like 20 years worth of old midterm exams from various different classes, all posted on the class website, linked from somewhere on the class website, right? I'm sure you've found it by now. There have been questions like this several times in the past, and I predict no comment on this semester, obviously, but certainly I have not made this question for the last time yet. At some point, again, I feel sure this will be an exam question. Again, no comment for this semester. So how are you going to do it? Now, by the way, a real quick check. Notice nowhere in the statement of the question does it say anything about continuous differentiability. Right? So it's going to be your job, right, to be heads up that whenever you need to check that something's differentiable, almost certainly the right way to do it is to think about continuous differentiability. Try to use this theorem right here. And here's how it applies. We got this function, and it's super easy to compute the partials. I mean, like really easy to compute those partials. So easy I don't even feel the need to write it down. I think that's pretty clear that they're all polynomials. Okay, next. Polynomials are all continuous. Yep. Right? I mean, no question there. Hey, check it. The partials are all continuous. That is the very definition of continuous differentiability. And we have a theorem that says continuous differentiability gives you differentiability. So, done. No nasty business with relative error and all that stuff. Yep.
Is the last word supposed to mean like they're all different or unique?
Different. So no, this is a big word. Differentiable means that let's see, the most efficient way to differentiable means that the linear approximation is a good linear approximation in the sense that that most naturally makes sense out of that statement. Yeah, it's a statement about linear approximations not being obvious garbage. Yeah, right. Yep.
What do you mean by partials exist? If partial is 0, does it not exist?
No, 0 exists. Yeah, but if you have a formula for the partial derivatives, and if that formula has, let's say, some polynomial in the denominator, any point where that denominator is 0, the partial derivative doesn't exist. Yeah. Right. So it's not about whether you can write down an expression that works most of the time. It's about, does that expression actually work and give you an actual value, a legal real number, everywhere in question.
Can you give an example where partial doesn't work?
Yeah, talk to me after class. But yeah, that's no problem. But let's see. I'm sure I can, but just not quite off the top of my head. Yeah, I saw a hand back there. Yeah.
Well, how do we show it's continuous?
By basically waving your hands and citing old theorems from high school, namely that every, let's see how to say this. Every polynomial rational function, trig function, log, exponential, I think that's pretty solid. Any function of that sort, any combination of those functions, products, sums, differences, quotients, anything you can generate out of basically any function you ever saw in high school is continuous where it's defined. Yeah. So in cases like this, I mean, we're talking about a polynomial here. Polynomials are obviously defined everywhere, so they're continuous everywhere.
So on example, you just said it's a polynomial.
Yeah. That's right. That's totally fine. Okay. Now one more thing I'll tell you about differentiability, and this is useful here and there, but this is it's okay. Whatever. Anyway, it is what it is. True fact. Not going to prove it, but every differentiable function is continuous. I hope this is believable. There's a single variable version of this. So this is just sort of a, extension of old news. And as this is written, it's not particularly useful to deciding on questions of differentiability, because differentiability is the hypothesis of this implication, not the conclusion. So you would have to know already whether the function's differentiable before you could even use this theorem. Not useful as written. But what we can do, and this is a really cool trick, I hope everybody's familiar with the idea called the contrapositive. If you're not, come to office hours, I'll be happy to flesh it out for you. All the contrapositive says is that if you have an implication, and keep in mind an implication says that when your hypothesis is true, that your conclusion must therefore be true as a result. Whenever you have an implication, you can kind of turn it upside down and backwards. As in, if the conclusion is false, then it must have been the case that the hypothesis was false. You just kind of have to sort of think that through. That, well, of course, because if the hypothesis had been true, that would mean that the conclusion would have had to been true, but here we're assuming it's false. You know what I mean? So it's a lovely little construction, very useful in a lot of ways. This is one of several ways that we'll use contrapositives in this course. And the contrapositive says this, and notice now our statement has as a conclusion a resolution of the question of differentiability. Right? If a function fails to be continuous, okay, definitely not differentiable. So here's an example of how we can use this. This is the example we talked about at the very start of today's class. This weirdo thing that's 1 above the axes and 0 everywhere else. Strange function. But it has an obvious discontinuity, certainly at the origin. Right? You look at the origin right there. Right? At the origin. As you approach the origin, the value of the function is 0, and then when you get to the origin, the value of the function is 1. So an obvious jump discontinuity, and if it's not continuous, then it's definitely not differentiable. Yep.
So like, if I say fx is equal to 1 over x, so at 0, that would be discontinuous?
Yes, that's right. That definitely has a discontinuity at the origin. Yeah. That's right. But it's also not defined at the origin. So there's trickier ways where you can have examples of functions that are defined but not continuous. This being one of them. Yeah. Right. Okay. So we're kind of done with all the. Oh yeah. Go ahead.
I just have one question.
Yeah.
Does this still apply to like piecewise functions?
One more time. I'm sorry.
Piecewise functions.
What about them?
Does this still apply to the continuity rule?
Oh, yeah. So this statement, in fact, both of these statements, they are true statements about whichever sets of points you're talking about. So when you're talking about a function that's piecewise continuous, you just don't talk about the point where it has a discontinuity, and you also don't draw any conclusions about the point where there's a discontinuity. Yeah, absolutely. Right. Okay, so we're kind of done with the formal nonsense, right? Now we're going to get back into some computations and developments of a little bit more tangible kind of ideas. So back to linear approximations. Y'all recall this formula right here. This was our most general linear approximation formula. And I'm going to do a slight massage of this formula, just a little bit, teeny tiny little change, hardly anything is going to happen. And here are the two things I'm going to do. First, Recall that a linear approximation has to agree with the function at the point where you're doing the approximation. So f of a is L of a. No big. And then I'm going to take the L of a that's on the right and I'm going to subtract it over to the left. No big. Right? Okay, so now let's look at what we have. And this is actually a really cool formula as it's written. This is a great statement about what df does. And I think this is a really big deal. I think it's a really important fact. That's why I'm about to spend 2 pages of notes talking about basically this one point. And that is, let's look at what df is doing. Notice that it's being multiplied by x minus a. That's how much we change in the input, right? When you're doing a linear approximation at a point A, and then you're looking at a nearby point x. X minus a is how much you've moved in the domain. This is what we call the input differential. And by the way, I really like this notation here, dx vector. I don't know if y'all have seen a differential that was a vector before. It's a little wild to think about, right? Because you're probably accustomed to scalar differentials. But all this means is a differential in position as opposed to just a differential in a scalar value. But it's still just a differential. How much did it change? Okay. And then let's look at what comes out on the left side of the equation. Now, this does not directly address f. This is about L. But if you think about it, L is our approximation of f. So when I say how much did L change, another way to say that is that's my estimate of how much f changed. It's not actually how much f changed, but it's my estimate of how much f changed. So that, in fact, is what we mean by an output differential. A differential, output differential anyway, is a linear estimate of the actual change. So back to df. What is df doing? df apparently is what I multiply by input changes to get output changes. Where have I heard that expression before? That was our shared defining characteristic of a derivative. Remember when we first started all this derivative stuff, I said all derivatives have this one thing in common. They relate input changes to output changes in their various different ways and their various different circumstances, blah, blah, blah. But it's always a relationship between input changes and output changes. And df does it as generally as possible. If you think about partial derivatives, well, you know, if you play this make-believe game where I pretend that most of the variables are actually not variables, right? In other words, in a hypothetical nonsense scenario, partial derivatives make sense. This makes sense no matter what. This dx vector could be any vector, any direction, any magnitude, whatever. The df matrix is what turns that input change into our corresponding estimate of the output change. So as I've got written here, because df is a thing that turns input changes into output changes, we call it the derivative. It is doing what derivatives are supposed to do in all cases. So the derivative. This is what I've been trying to stop myself from saying for the last, lecture or two, however long it's been. I didn't want to call this the derivative matrix just yet because I wanted to be able to justify it before I started using that terminology. Here's the justification. And so, so we're going to start calling this the derivative, aka the derivative matrix, and of course matrices are linear transformations, so sometimes it's called the derivative transformation. Okay, how we doing? Everybody with me? Okay. All right. A quick little notational point. It's also sometimes written as JF. J is for Jacobian, which is a reference to a mathematician named Jacobi. So, you could write it as JF or as DF. This book uses DF. It doesn't matter. It's just notation, right? I point this out just in case y'all see the derivative matrix outside of this course, right? A certain fraction of the time you see the derivative matrix, it'll be written as JF. Okay. So, picture what's going on geometrically when I write this down. That the DF matrix does this task. Well, keep in mind the input differential is a vector that represents a change in position. The output differential, DF, is a vector representing a change in the output value. And as drawn here, what DF does, big DF, is it turns that input differential into this output differential. Now, I do want to make sure to distinguish differentials from points, right? F is the thing that takes input points and turns them into output points. So here's an input point A, and here's the corresponding output point F of A. The thing that turns the input point into the output point is F. F takes points to points. DF takes vectors to vectors. Everybody okay with that? Okay. All right, now here's a twist. Another little easy, very slight little massage of the equations to give a nicely different interpretation. I am going to take what we had before and divide by dt. So there you go, dividing by dt. Right, you recognize this is the equation that we had before. Divide by dt. Now you get this. What sense can I make out of this equation? Okay, well, let's think about dx dt. I mean, it's the derivative. It's not a differential, right? It's the derivative. And I'm going to address the following interpretation more soon. I'm not going to quite have time to do it today, but soon we will make a reasonable case that just like in single variable calculus, the derivative of position is velocity. I hope you all remember that from single variable calculus. One of the really nice applications of calculus to physics. Derivative of position is velocity. Likewise, then, on the other side, derivative of the output position is the output velocity. So now again, check it out. DF again is relating inputs to outputs. This time, not differentials to differentials. This time, velocities to velocities. Both, though, still represented with vectors. Right? So now it looks like we've got the same picture as on the previous page here, but it's not. Well, I guess artistically it is. But we're taking a different interpretation. Here we're not thinking of DF as turning input differentials to output differentials. Here we're thinking of DF as turning input velocities into output velocities. And I actually like this interpretation better. And I'll tell you why. When you're thinking about differentials, there's no getting around the fact that this is an estimate of what's actually happening to the function. It's just an estimate, so there's going to be a little round-off error, and no, it's just not quite right. Okay, fine. Not so here. This is exact. This is literally the exact derivative, the exact velocity of the output. Because it's all instantaneous, right? You take a derivative. Derivative means limit as dt approaches 0, etc. So here you don't have to sort of constantly apologize for the fact that it's an approximation. We have literally a relationship between input velocity and output velocity, and I think that's nice. Yeah.
Is DF a vector or a
matrix? Matrix in general, yeah. Here it's a 2x2 matrix because you can see it's got it's multiplying by a 2-dimensional input vector and it's producing a 2-dimensional output vector.
But like DF is like the D matrix times the F A vector, right?
DF is itself the matrix. Yeah, there is no D. There is no matrix called D.
Gotcha.
Yeah, DF is the name of the derivative matrix. Yep. Yeah. Okay. Okay, now, some of you may be thinking, hey, wait a minute. Didn't you say that for real valued functions, we do linear approximations with gradients? And that's true, right? We wrote down a formula for linear approximations with gradients. If you go through the same kind of argument that I just did, but with gradients, then you get this equation, which, again, you might want to interpret as saying gradient, specifically dot product with the gradient, turns input differentials into output differentials. So which is it? Is it the gradient? Do I have to use gradients for the real valued case and DF matrices for the vector valued case? And the answer is use whichever one you like in any situation where it makes sense. This only makes any sense at all for the real valued case. And in the real valued case, let's see here. Wrong color. In the real valued case, the DF matrix has only a single row, and matrix multiplication by a single row matrix and dot product with a vector are computationally identical. Right? Flashbacks to Math219, right? But basically, how do you if there's a single row here for DF, how do you do row dot column? Well, yeah, it's the dot product, right? Here, this is literally already the same exact dot product. So this is a superficial distinction only. You have to use the matrix, obviously, when you have vector valued functions. When you have real valued functions, take your pick. It's just purely a notational distinction. Yeah.
What if you just transposed it? Like, what would happen to it?
Transpose DF?
Yeah.
Okay, well, yeah, you can't.
Oh, you
No, the DF is strictly, you as a matrix, it is arranged the way it is.
Okay,
yeah.
okay.
No, maybe what you meant was if you take that row, that is, the DF matrix, take that row, look at the individual elements, and then reassemble those elements as being a vector. Yes, it's literally exactly the gradient vector.
Okay.
Yeah.
Got it.
Yep. Okay. All right. So reinterpretation, this is the same thing, but reinterpretation in the real valued case, which we're addressing here, so a single output only. In the real valued case, yes, we're turning input vectors into output vectors. And you can think of the thing that does that as being the derivative matrix as we have before, or you can think of it as being dot product with the gradient as we are here. Okay, a couple things to say about section 2.4. A lot of this is highly readable, so please do make sure to read section 2.4. In general, please make sure to read all the sections of the book as we go through, right? I'm hitting the most interesting, most challenging, most discussable ideas only, because in the interest of time, it's just not possible to do it all. So again, you're always reading the book, but in particular, make sure to read what's in 2.4, because a lot of it is important but doesn't need to be discussed. It's all highly readable. And I want to talk about the act of differentiation. I claim that differentiation is linear, by which I mean this process, the process by which I take a function and I compute its derivative matrix. Right? That's what differentiation does. You give me a vector valued multivariable function. I produce the derivative matrix. That is what it means to take a derivative at this point. Right? And I claim that process is linear. This is not as obvious as it looks. There's a temptation to confuse the act of differentiation with the result of differentiation. And yeah, sure, the result of differentiation is the derivative matrix, and of course that's linear. It's a matrix. All matrices are linear. That part is clear. The distinguishing statement that I'm making here, and again, really not obvious, true but not obvious, is that not only is the result of differentiation linear, but the act of differentiation is linear. So it's not just that when you take linear combinations of vectors and multiply by a matrix that linearity happens as it should. It's that It's that if you take linear combinations of functions, like I have here, differentiation acts as it should. It's a very different statement. So I want to show you just an example of this. I'm not going to prove this fact, but I think this example is highly satisfying. Here's a function and its derivative matrix. Make sure you can do that. Okay. Here's another function and its derivative matrix. Again, make sure you can do that. Here I'm taking an arbitrary linear combination of those two functions, coefficients 5 and 6, because I wasn't feeling creative with the numbers. Doesn't matter. It's just an example, right? You can take that linear combination, that is a function, and you can write its derivative matrix. And again, it's just a matter of writing down the appropriate partials. Nothing spooky happening there. Okay, boring. So where is the linearity of differentiation? Well, notice this is the derivative of the linear combination. This is a linear combination of the derivatives, right? I looked at individual derivatives and did the same linear combination of the derivatives. On the right, I did the combination and then the differentiation. On the left, I did the differentiation and then the linear combination. Doing it in the opposite order. And I'm going to leave it as an arithmetic exercise for y'all to confirm that, yes, sure enough, you do indeed get the same thing. So this doesn't prove anything, but this is just an example of what we're talking about when we say that differentiation is linear. Is that cool? Everybody happy? Takes a little digesting, right? Okay. Another little quick comment. There are a couple of different product rules and a quotient rule, and this is all in the book. It's all highly readable. You can check by direct computation by coordinates that this works. Take a look. Again, this doesn't rise to the level of needing a discussion, but it is stuff that you should know, and very handy formulas you don't want to go without. Okay, higher order partials. Think back to single variable calculus. We talk about derivatives in single variable calculus, and you can take a derivative of the derivative. That meant something too, right? It had some nice geometric interpretations. All right, well, same here. Here's some partial derivatives, x partial, y partial. Y'all know how to do partial derivatives. Y'all remember these notations, I presume. Okay, and as discussed, now we're going to take derivatives of this derivative. On the one hand, I can talk about taking the x partial of that x partial. And I can talk about taking the y partial of that x partial. And likewise over here. Really, the main thing I wanted to talk about on this, before we'll wrap it up in just a quick second, is the notation. And this is a little awkward, and it can be confusing. I'm going to try to persuade you that, unfortunate though this notation is, it is the best choice. And here we go. We'll start off by thinking about the x partial. Now, here's one way to write the x partial, the Leibniz-like notation. Here's our Newton-like notation for the x partial. How would I represent taking the y partial of that? Well, okay, there's how we take the y partial using Leibniz-like notation. We say d by dy on the left. And here's how we do it with that subscript notation. We put the y subscript on the right. that's our hands are tied. That's what they told us that we have to do. This is just the standard notation. One's on the left, one's on the right. It's super annoying. But having observed that, notice that you really kind of have to put the partial y, partial x in that order there, but the subscripts you really kind of have to write like that there. And let's see, let me zoom so we can see this better. And so what really stinks, not my fault, don't blame me, but the y is on the left there, but the right here. And it's on the right here, but the left there. And it's enough to make you want to tear your hair out, right? But the alternative would be to have, how would you feel about writing this as fyx? I think that would be outrageous, right? And likewise, the other alternative, I suppose we could put the partial symbol that's on the left over there, we could put it on the right over here. Again, I think that would be outrageous. So weird though this is, right? This is a little bit of a bummer, but I think it's the least bummery of our bummer options. And so just heads up, different notations, different orders. Y'all have a good day. See you later.